Alright, welcome back. This time we're going to be talking about a concept which is closely related to that of subgroups, namely cosets of a subgroup. So we're going to introduce the concept, prove some theorems, give some examples, and then near the end we're going to reformulate it in an entirely different perspective, which will help us going forward. Alright, suppose we have a group G, a subgroup H, and some arbitrary element A in the group G. We can make a special product between this subgroup and this element in the following way. If we say HA is the set of all elements little h times A, such that H is an element of the subgroup, so we take our one singular element A and then multiply it by every element in the subgroup H to form some set of elements. It need not be a group, right? But it will be in G. This is going to be known as the right coset. So the right coset of H in G, or a right coset, right? Because we could let this element A vary and we might get a different set. So we'll call that a right coset, and then we'll call a left coset basically the opposite. We take the element A and multiply on the right by every possible element in the subgroup H, and this gives us the left coset of H in G. Or once again, it is a left coset of H in G, as we may get different cosets, and generally we do, for different elements A in the group G. Now this is one of those concepts in group theory where if you've never seen it before, it seems a little odd that we would take an entire subgroup and multiply it through by one element. Like, how would this be useful? So this is one of those things we really need to motivate well. So I'm going to do some examples of these cosets so you can see what's happening inside the group. Alright, let's start by looking at a group we're pretty familiar with by now, namely Z8, so the integers under addition modulo 8. And then let's look at the subgroup, which I'm going to call H, equals 0 and 4, right? They form a subgroup with just that element being idempotent. 4 plus 4 is 8, mod 8 is 0. And what we want to do is form cosets. Let's just restrict ourselves right now to left cosets. Alright, so what we want to do is take some arbitrary element, how about 1 for the moment, and we're going to add it to every element of H to form a coset, right? So when I showed you before, I said A times H is a left coset of H in G, or in Z8 in this case. Of course, if we're in an additive group, as we are right now, we would write this as A plus H. So I can write the coset 1 plus H is equal to, and then it's going to be 1 plus 0 and 1 plus 4, right? Which is going to be 1 and 5. All right, let's do the same thing with the element 2. 2 plus H is going to be 2, 6. 3 plus H, another coset, is going to be 3 and 7. And then 4 plus H is going to be equal to 0 plus 4 is 4, and then 4 plus 4 is 0, right? But this is actually our subgroup H, right? It's just we reverse the orders, but it doesn't matter. So that this is equal to H. And if you continue this, doing 5, 6, and 7, and of course 0, which 0 plus the subgroup is going to be the subgroup, you're only going to get these 4 again. So that we have 4 different left cosets of H in the group Z8, namely the subgroup itself, this one, and this one, right? This is the subgroup. Now likewise, we can form right cosets of H in Z8, and we can do this just by adding on the right. But since addition modulo 8 is commutative, we notice that adding on the left and adding on the right by this one element is not going to change anything. So that means that this is equal to 1 plus H, this is equal to, H plus 1, this is going to be equal to h plus 2, and this is going to be equal to h plus 3. So we have this relationship here that 1 plus h is equal to h plus 1, and in general for any element in this group. However, this is not in general true, but it is true of abelian groups, which leads us to our first theorem. So let G be an abelian group and H be a subgroup of G. Then for all elements in G, AH is equal to HA. The left coset is equal to the right coset if G is an abelian group. Well, this is pretty straightforward. AH is defined to be the set of all A times H, right, for elements in this subgroup. Well, if the group G is commutative or abelian, then we can rewrite this as H times A for all H in the subgroup, and this by definition is the right coset of H and G. Alright, as our second example, let's look at multiplying real numbers without 0 as a subgroup of the multiplicative complex numbers without 0. Alright, well, if we want to take cosets of H and G, we need to first pick some arbitrary element in G, which we were calling A before. Let's call it A plus BI, right, because it's in general a complex number. And we're just going to say that this is not equal identically to 0 because that wouldn't be in the group. Alright, now let's draw a picture to help. We have our x-axis, our y-axis, and we have some point A plus BI, which we can think of as this sort of vector here in the complex plane, right? So what we can do now is we can take a coset of this subgroup in G via this singular element. All right, so what happens if we multiply this by any non-zero real number? Well, what you're going to end up with is something which has the same angle. If you recall that the angle made with the x-axis is going to be equal to the inverse tangent of the imaginary coordinate over the real coordinate. Well, if you scale them by the same amount, then those factors are going to cancel out and it's going to remain the same. So what we're going to get is a line, but not exactly a line because we are not including the origin. So we have that a coset of the multiplicative real numbers in the multiplicative complex numbers without 0 constitutes a line with 1 point missing. So you see this time there are actually going to be an infinite number of cosets, right? With the cardinality of the continuum, because you have one for every possible line going through the origin in the complex plane, minus the origin itself, of course. Something of note I'd like to point out here is that none of these lines intersect anywhere. If they were going to intersect somewhere, it would be at the origin, but our group doesn't contain the origin. So that our different lines, even though they're infinitesimally close, if you like, they are disjoint. They don't share any numbers. Alright, for our third example, let's look at the special orthogonal group inside the orthogonal group. So if you recall, the orthogonal group is those set of matrices in the general linear group that have the property that M times its own transpose is equal to the identity, or its transpose is its inverse matrix. And the special orthogonal group is the refinement of that to those matrices which have exactly determinant positive 1. Because a matrix could also have determinant negative 1 and then determinant of M times the determinant of M transpose would still equal 1, right? So these could have determinant plus or minus 1, but these have to have positive 1 determinant. Well, if we want to look at cosets of this group in this group, then let's just look at a general matrix in the orthogonal group. Well, obviously, for any M in O of n, M times SO of n, right? The left coset of SO of n in O of n is going to be, clearly it's also going to be an orthogonal matrix because this is closed, but we also notice that for any matrix here, we have determinant is equal to 1, so that the determinant of the product matrix is equal to the products of the individual determinants is going to be equal to whatever this is. And since we know that it can only be plus or minus 1, we see that there can only actually be two cosets of the special orthogonal group in the orthogonal group. Namely, there are those matrices which have determinant positive 1, so SO of n, if that's positive, and what I'm just going to casually refer to as negative SO of n here, well, that's probably bad notation, for determinant which is negative. It's those matrices which have exactly determinant -1 in the orthogonal group. So there's only two cosets here, even though there's definitely an infinite number of elements in the group. Alright, next theorem. So, two left cosets, equivalently two right cosets, are either equal or mutually disjoint. Of course, we're talking about cosets of the same subgroup in the same general group G, H and G, as we were using earlier. Alright, so suppose that X is an element in the intersection of two different cosets. Then we know that X can be written like this, and it can also be written like this, right? As A times an element from the subgroup, or as B times an element from the subgroup. Now we can set these two expressions equal, right? AH1 is equal to BH2, and this gives us two things. It gives us an expression for A in terms of B and H's, and the other way around, so that we have A is equal to BH2 H1 inverse, and B is going to be equal to, likewise, A H1 H2 inverse, right? Alright, now we're going to let two arbitrary elements of our group G be such that G1 is in the left coset of H and G by A, and G2 is in the left coset of H and G by B. Now, we have then that G1 has to be equal to A times some, let's just call it H prime, some H value. But we know that A is equal to B H2 H1 inverse, so this is times H prime. This is going to be another element which is in H, and hence B times some element H is some element in the left coset of H and G by the element B. So that means that G1 has to be contained in BH. Likewise, G2 has to be able to be written B times some H star, we'll say, and B we have an expression for is equal to AH1 H2 inverse H star, and then this is going to be another element in H, so that G2 has to be in the left coset of H and G by the element A. So if an arbitrary element in this set is in this set, and an arbitrary element in this set is in this set, then we conclude that AH is equal to BH. They are the same coset. So we have that AH equals BH, or AH intersect BH is the empty set. And we have our theorem. They're either equal or mutually disjoint. Alright, next theorem. So if G is a group and H is a subgroup again, then the group G is the union of all left cosets of H and G. Equivalently, it is equal to the union of all right cosets of H and G. Alright, so to prove this, let's suppose we have some collection of left cosets, which I'm denoting A sub I times the subgroup H, such that this is all the left cosets of H and G. Now, let X be some element in G, but not in the union of these cosets. So, G without that union. Then, for all elements H in the subgroup H, there does not exist any element Y in G such that x is equal to yh, right? Otherwise, x would by definition be in this coset produced by y. But this contradicts our assumption that G is a group, because in a group, whenever we have two of these elements, the third one is uniquely determined. So there must not exist any such element x. So we conclude that this is indeed a non-empty set, an empty set, and G is equal to the union of its left cosets. And you can do the same thing with the right cosets. All right, let G be a group and H be a subgroup. Then the cardinality of a left coset is equal to the cardinality of a right coset, which is also equal to the order of our subgroup we're taking cosets by. And notice I said cardinality and not order, and that's because a coset cannot be a subgroup unless it is the identity coset, right? Just that subgroup H. The reason for this is that they have to be either equal or mutually disjoint. And if they're disjoint, then only one of them can contain the identity element, and every subgroup has to have an identity element. All right, so how do we show this? Well, recall that AH is equal to all products of this form, right? Well, we notice that this is going to form a set AH1, AH2, all the way up to AHN if it's finite, or just keeps going. And so that this set in general has a cardinality equal to that of H, except for the possible case that two of these are equal. So if we were to have AH sub I is equal to AH sub J, then, well, this is a group, G is a group, so we can cancel on the left and we'd have to have HI is equal to HJ, which obviously doesn't make any sense, so that it is true they have to have exactly equal cardinality. All right, next theorem. If R denotes the set of all right cosets of H and G, and our script L denotes all the left cosets of H and G, then the cardinality of the two sets have to be equal. In other words, there have to be the same number of left cosets as right cosets. All right, so to prove this, we want to construct a map from the set of all right cosets of H and G to the set of all left cosets in H and G. And we're going to do this by calling f of H times A equal to A inverse times H on the left. So now let's suppose f of HA is equal to f of HB. We want to show that this is going to be a one-to-one mapping. So A inverse H is equal to B inverse H. And that means that there exist H1 and H2 in the subgroup H such that A inverse H1 is equal to B inverse H2. Now we can do a similar trick to what we did before, so that we have A inverse is equal to B inverse H2 H1 inverse, and we're going to have B inverse is equal to, on the other hand, A inverse H1 H2 inverse. All right, now let's suppose that X is some element in this right coset here, HA. That means that X can be written as some H3 times A, right? Well, we know though that A inverse can be written in this way, so that this is equal to H3 times the inverse of this, so B inverse H2 H1 inverse is going to be equal to H3 H1 H2 inverse times B. But now this, again, H3 times H1 times H2 inverse, these are all elements of the subgroup H, which is closed, so this is going to be some other element in the subgroup as well, and so that we have this can be written as X is equal to some H star times B, which means that it's also in the right coset with respect to B here. So X is in HA implies X is in HB. And we can do the exact same argument with substituting the other expression instead to show that x in HB implies x is in HA. Thus, we get at the end that the two sets are equal, and we had that f of this coset is equal to f of this coset implies that the two cosets are equal. In other words, our function is 1-to-1. All right, now for all left cosets, there's going to exist a right coset such that f of HA is equal to BH. Namely, HA is going to be equal to HB inverse, right? Because HB inverse maps to B inverse inverse H, or just BH. And we're guaranteed that this element exists because we're in a group, so B has an inverse, and so the coset is well defined. Thus, our mapping is both onto and 1-to-1, and thus it's a bijection. And whenever we have a bijection, then the domain and codomain have to have the same cardinality. In other words, the cardinality of R is equal to the cardinality of L. Now, the fact that for some arbitrary subgroup that it's not in general true that HA is equal to AH, right? The left coset may not be equal to the right coset, but yet there's this invariance of the number of total cosets there are, right? The number of right cosets has to be equal to the number of left cosets. This would suggest to us that this number, the number of cosets of a subgroup in a group, is an important number, and indeed it is. We have a special name for it. The index of a subgroup H in G, right? So G is the group, H is the subgroup, and we're looking at the index of the subgroup in the larger group, is the number of total cosets, right? Equals number of total cosets of H in G. And we denote this as G colon H in square brackets. The index of a subgroup. All right, here we have a pretty important theorem. So if K, H, and G are groups, such that K is a subgroup of H and H is a subgroup of G, and of course transitively K is a subgroup of G, then we have that the index of K and G is equal to the index of K and H times the index of H and G. All right, so I'm not going to prove this, but I am going to give an illustration using the group Z12, right? Addition modulo 12. So we have these 12 elements, right? And then we're going to have a first subgroup, which we're calling H, and it's going to be just the even numbers in there. And it's easy to verify that that is indeed a subgroup. And then this is a sort of sub-subgroup, right? Because this is contained in that, and that's contained in that one. This is just 3 elements, 0, 4, and 8 under addition modulo 12. And this theorem says then that because we have this nested group structure going on here, that the index of this and this times the index of this and this has to be equal to the index of this and this. And what are those indices? Well, if we look here, if we add 0, 4, or 8 to this set, on the left or right, since it's commutative, we're going to get just the same subgroup. Or if we add 2, 6, and 10, we'll get some permutation of 2, 6, and 10, so that there are only 2 cosets of K and H. So the index of K and H is going to be equal to 2. Likewise, the index of H and G is going to be 2 as well, because we're going to have that we could add an even number or an odd number, and we're only going to get 2 cosets out of that, so that this is equal to 2. And so by this theorem, this predicts that the index of K and G should be equal to 2 times 2, or 4. Is that the case? Well, we can think about adding mod 4 here, because what we'll have, we start here, here, and here, and then add the element 1 to that whole set. Well, that'll shift us 1 over. Add 2, it'll shift us 2 over. Add 3, it'll shift us 3 over. Add 4, and that'll be there, and this will loop back, and we'll end up with our subgroup again. And it is true. We do have an index of K and G being equal to 4. All right, so now I think we finally come to our first named theorem. So Lagrange's theorem says that if H is a subgroup of a group G, then the order of G is equal to the order of H times the index of H and G. To see this is true, we just apply the last theorem, where we had that if K is inside of H is inside of G, these are all groups of course, then the index of K in G is equal to the index of H in G times the index of K in H. And then what we do is we just set K to be the trivial group. So if we set K to be equal to the identity group, right, the trivial group, then this just becomes the order of H, right? Because the identity, by definition, times each element in a group, or subgroup in this case, is going to be equal to that element. So that we're going to have the same number of elements, and in fact it's going to be the exact same set even, as is in the subgroup H. It's going to be the order of H there instead of the index of K and G. And likewise here we're going to have the order of G, because the identity element times every element in G, the same thing is going to happen. You're going to get just every element in G. So we get this as a special case of the last theorem. As a corollary, it's true that for all elements in the group G, if the order of G is finite, then we can take this element A, generate a cyclic group, and the order of that cyclic group must thus divide the order of the total group. So we have a number theory property, really, a divisibility property here relating a group to one of its elements, which is popping out of this theorem. All right, here's another theorem which will make a great exercise for you to prove yourself. If H and K are both subgroups of the group G, with K and H both finite, then the order of this, or cardinality if you like, is equal to the separate orders of H and K divided by the cardinality of H intersect K. And we're defining H times K, right? This is a subgroup sort of times another subgroup in sort of the obvious way. All pairings of this form, H times K, such that H is in the subgroup H and little k is in the subgroup K. This is a good one for you to verify on your own. Okay, so now we're going to define congruence modulo H, where H is still a subgroup, to mean that if two elements are right congruent, we'll say, mod H, that means that A times B inverse is in the subgroup H. Likewise, A is left congruent mod H to B if A inverse times B is in the subgroup H. Alright, so our next theorem is the congruence modulo H, left or right congruent, is an equivalence relation on G. And in fact, I'll show it holds for right congruence, but you can do the same thing to show that it holds for left congruence as well. Alright, so to prove this, we got to show that it satisfies the three equivalence relation axioms. So first, we got to show that for all elements in the group G, say for all A and G, we want to show that A is congruent, and we'll do right congruence. A is right congruent to A. Well, for all elements A and G, we do know that A times A inverse, which has to exist because we're in a group, is equal to the identity of the group G, but the identity of the group G has to also be, by uniqueness of the identity element in H, the subgroup, so that A times A inverse is in the subgroup H, and by definition then, A is right congruent to A mod H. So we have that it satisfies the first axiom. Alright, for our second axiom, we have to show that it's symmetric. So suppose that A is right congruent to B mod H. Well, this implies that A B inverse is in H. But H is a group, right? It's a subgroup, which means that it contains its own inverses. Therefore, AB inverse must also be in the group H. And this is by the way we do inverses. It's going to be B inverse inverse, or just B, times A inverse. And that has to also be in H. Well, by definition then, this means that B is right congruent to A mod H. So it satisfies the second axiom of equivalence relations. All right, now for the last one, suppose A is right congruent to B and B is right congruent to C. That means, by definition, AB inverse is in H and BC inverse is in H. But what does this mean for the product? Well, if for any two elements in a group, it's closed under the binary operation, so that their product must also be in that subgroup H. So AB inverse times BC inverse must be in H. But by associativity, we can change the order of the parentheses, and B inverse B are going to annihilate, and we're going to get an identity element, so that this is just A times C inverse. And we said it has to be in the subgroup H, and by definition this means that A is right congruent to C mod H. So it satisfies all three axioms of an equivalence relation. So just as an equivalence relation induces a partition on a set, we have that an equivalence relation on a group induces a partition on the group. And more importantly, this partition is the set of all cosets, which we showed by other means have to be disjoint, right, or equal. These are the equivalence classes under an equivalence relation. And this begs the question, well, one, can all of algebra be reduced to relations on sets? And in some sense, the answer is yes, if you're taking the set theory approach. And then the other question we might wonder is, what if we beef up our relations a little bit? So next time, we're going to be talking about normal subgroups. And normal subgroups are exactly what happens when we take this equivalence relation on a group, which partitions it into cosets, and we give it the further property that it is a congruence relation on that group. Then the equivalence classes of this congruence relation, or congruence classes if you like, actually form elements of a group themselves.